So let me start it officially again. So good morning, students. This is a class of geotechnical engineering. So we are uh, in module 2, part 2, that is seepage of water. So in the last class, we have discussed about two-dimensional flow of water or flow of fluid through a porous medium proposed by Laplace. So it is also known as a Laplace equation of two-dimensional flow. Okay, so we already discussed about it. And if you remember, in the at the end of the Laplace equation, or you can say in the Laplace equation, uh, a new parameter is introduced to you, that is velocity potential, if you remember that. So if you remember the equation of Laplace, what is that? Double derivation of velocity potential with respect to distance, or say the double derivation of phi, that is velocity potential, with respect to x direction, plus double derivation of velocity potential with respect to y direction. The summation is equal to 0, isn't it? So what is velocity potential? It is denoted by phi. And how can you find out velocity potential? It is a multiplication of k into h, where k is your coefficient of permeability and h is your total head difference, or you can say head due to which water flows from one point to another point. Okay, so phi is equal to k into h. That is the equation we already discussed in the last class. So we are going to discuss about velocity potential today in today's class also. So we're going to discuss about velocity potential and stream function, and we'll end the class with discussing about flow net and some property of flow net. Okay, so let's go to the sharing of my screen. Okay, let's wait. So my screen is visible, right? Please to respond. Okay, so let's yeah, so I want to go through the last class only. You can see this particular final result of last class, that is Laplace equation, double derivation of phi, where phi is what? K into h. K into h means phi is your velocity potential. Double derivation of phi with respect to direction x plus double derivation of phi with respect to y direction is equal to summation of that particular thing is equal to 0, and this is known as Laplace equation. Okay, but the general equation is this one, number 2, del square kh divided by del x square plus del square kh by del y square equal to 0, where k into h represents your velocity potential in respective direction. Okay, so yeah, in addition we also discuss about for isotropic soil. For isotropic soil, your all properties, elastic properties are same in all mutually perpendicular direction. So we can say in case of isotropic soil, kx equal to ky. So you can cancel out that k value in a particular equation, that means from equation number 2. And for isotropic soil only, we can rewrite or modify the equation by this, that is del square h by del x square plus del square h by del y square equal to 0. It is double derivation of total head difference in a direction x plus double derivation of head difference to the direction y equal to 0. Okay, so these things already discussed in last class. Okay, so today we'll start with discussing about velocity potential again. It's a very simple thing to understand, so don't make it so complicated, don't think too much, just a simple mathematical term. Okay, it's all now become mathematical. So you know that phi is equal to what is velocity potential phi, denoted by phi, and it is given as k into h. Okay, this is one, you can say the definition of phi. Okay, but there is another definition for phi based on its significance. So what is this? So velocity potential may be defined as a scalar function of space and time such that its derivative with respect to direction gives the fluid velocity in that direction. That means if you derive velocity potential with respect to any direction, okay, somebody is waiting, so let me first unlock my meeting. Yeah. So what is this statement means? If we derive, or we can, if you go for derive or derivative or differentiate, you can say velocity potential with respect to any direction, the final result of that particular mathematical equation, that is derivation of phi with respect to any direction, it will give the velocity component of water, a fluid velocity component in that particular direction. Okay, that means del phi by del x, if you can go by mathematical term, by mathematically we can write del phi by del x, that is derivation of del phi with respect to del x direction. If you go and solving this, what we will get? In place of phi, if you can put the value of this, that is k into h, just put k into h, where k is a constant term in a particular direction. Okay, so let's take k in separate. Okay, then it will become del h by del x. Now what is del h by del x? It is simply hydraulic gradient in that particular direction, that is Ix, isn't it? So hydraulic difference, head difference divided by the length traveled by the water in x direction, that is del x for smaller section. So del h by del x, we can write it represents your hydraulic gradient in x direction. So now, since you know Laplace equation, accept or consider Darcy's law. And what is Darcy's law? V is equal to Ki. Okay. Now, since here you can see K multiplied by hydraulic gradient in x direction, so we can write it's simply give velocity component in x direction. V is equal to Ki, but since x is represents here only strictly for direction x, so here we have to write x, Vx. That is velocity component in x direction. So if you relate the first and last term, we can say that the derivation of velocity potential with respect to x direction, it gives uh, fluid velocity in that direction, Vx. Similarly, derivation of velocity potential in with respect to y direction, it gives velocity component in y direction only. So this is the very important significance of velocity potential phi. You have to remember this. Okay, so this is, you can write equation number 1, this is equation number 2. Okay, so this is velocity potential. Now let's discuss stream function. So stream function is also one kind of a parameter similar to velocity potential, but little different. Okay, let's discuss about stream function now. Hold on a second. Okay, মই ক্লাছত আছো ক মই এই ক্লাছটো কৰিলৈকে যাব পাৰিম। Okay, sorry. Yeah, so let's discuss about stream function. So you can see, if you can look closely, the definition is almost similar, but slight difference. Okay, so here, that by as per definition of stream function, and which is denoted by xi. Okay, this symbol represents xi. Okay, so stream function, it is defined as the scalar function of space and time such that a partial derivative of this function with respect to a direction gives a velocity component in a direction positive 90-degree clockwise to the original direction. Okay, so little different in the last statement. Okay, it's maybe look like little complicated, but it is very simple to understand. Okay, now I just want to elaborate these things from this diagram. Okay, now here you can see, if you imagine one graph paper, in this horizontal direction represent x direction, and vertically upward direction y. Okay, and vertically downward, you can imagine this is negative y, and here in the left side of horizontal direction represents negative x. Okay, and this point represents 0. Okay, this all the representation of direction. Okay, if you start from this, taking this center at this point at 0, in this direction take positive x, in this direction negative x, upward direction positive y, downward direction negative y. Okay, positive y, negative y. Fine. So as per the statement here, sorry, as per the statement given for stream function. So if you derive, or if you go for partial derivation of this xi, that is stream function, with respect to any direction, say y. If you derive stream function with respect to this direction, that is y direction, you will get velocity potential in clockwise positive 90-degree direction. That means if you derive xi in y direction, you will get, you can see the arrow. Since this arrow represents your 90-degree, from y to x, this represents the angle is 90-degree. Here also 90-degree, but we have to go clockwise, positive clockwise. So we have to go in this direction. And what about the axis we reach? Here, what reach? X, positive x. So we'll get velocity potential in that direction only. That means Vx. Got it? So if you can derive xi, or if you can derive a stream function with respect to y direction, we'll get Vx, which is in x direction. Okay. Next, if you can derive xi with x direction, that means if you can derive xi with respect to x direction in this direction, same concept, we have to go clockwise 90-degree below downward. Since it is clockwise, right? We cannot go from here to upward direction. Become anti-clockwise. Okay, so we have to go clockwise 90-degree. So if you can derive stream function with respect to x direction, you will get velocity potential in y direction in downward direction. That means, okay, and since this downward y represents negative, so you have to put a negative symbol here. Okay, so we can write Vy equal to minus delta xi by del x. So we can also write indirectly del xi by del x equal to minus Vy, just replacing the negative symbol. This negative only represents your direction. Okay, fine. So del xi by del x is equal to minus Vy. Okay, you can give equation number 3 and equation number 4. Now, from the all four equation, that is equation number 1, 2, 3, and 4, comparing 1 and 3 and comparing 2 and 4, that means 1 and 2 for velocity potential, 3 and 4 for stream function. Just if you can compare, you will get a relation between stream function and velocity potential. Okay, velocity potential and stream function, that is del phi by del x equal to del xi by del y, and del phi by del y is equal to minus del xi by del x. So this particular equation is known as Cauchy-Riemann equation. Okay, also remember this, the name of the equation. These two equations are known as Cauchy-Riemann equation. Okay, so this is all about velocity potential and stream function. Okay, so after these two definition, that is velocity potential and stream function, let's discuss about the graphical representation of these two parameters, and that particular thing is known as flow net. Okay, so I just want to go back to that first image. Here you can see, yeah. So the solution of Laplace equation gives sets of curves. They are known as equipotential line and streamlines. Okay, so this particular equation of the particular Laplace equation can be represented graphically by the use of flow net. Now, what is flow net? Flow net is, it's a kind of, you can say it's an imaginary line. Okay, flow nets is a kind of an imaginary line, or imaginary sets of line. Okay, join mutually perpendicular to each other. Okay, and this particular concept of flow net is very important to study the seepage of water through dam structure. So most probably, if you're going to construct any dam structure or hydraulic structure across the river, Okay, so if you know that since you are constructing a hydraulic structure across the river, that means you have to hold water in particular upstream phases. So that particular storage water may give some immense pressure to the downward direction and lateral direction to the structure. And water always try to seep or flow through the dam material. And that particular flow of water is known as seepage. Since we are discussing about seepage only in this particular chapter. Okay? So to study the seepage of water through a dam structure, which is very important for stability of the dam structure, since if seepage can pass through the downstream phase of the dam, it may collapse. It may cause collapse of the dam structure or may uh, cause failure of the dam structure. So we need to study the seepage of water, a seepage flow of water through a dam structure, and for that we can also use the concept of flow net. Flow net is it's a very important concept where it is used to study the seepage of water. Okay, now it's an imaginary line. Okay, first of all, I just want to clarify that it is an imaginary line. It's only used to study the seepage of water. Now, this flow net is a combination of two mutually perpendicular lines. Okay, one line is known as streamlines or flow lines, and another perpendicular lines are known as potential line or equipotential line. Now let's first discuss what is streamline. Streamlines are the path along which the individual water particles seep through the soil are called streamlines or flow line. That means if water flowing in this direction, that means from left to right or right to left, whatever you say, okay, along the direction, the line drawn are known as streamline. Okay, along the streamline, water particles flow. Okay, and what is equipotential line? Equipotential lines represents a contours of equal head or equal potential. Okay, and the direction of seepage is always perpendicular to the equipotential line. That means if the flow is in this direction, potential line must be perpendicular to the flow direction, and the streamlines is always parallel to the flow direction. This is the very basic difference. Okay, and why it is called equipotential? So you know water flow because of some gradient. Okay, that means there must be some head difference. Suppose the head, the total head at this point is 10 meter. Okay, from the reference point, and the head of this point is 5 meter from the reference point. So obviously water flow from higher to lower, that is 10-meter height to 5-meter height. So water is flowing in this direction. And what is the head difference? 10 minus 5, that is equal to 5 meter. That means because of the total head loss of 5 meter, water flow from left to right, or you can say in this direction. Okay, and that particular 5 can be divided some equal zone. Okay, say I'll give you some different example. Say total head difference is 9. Okay, suppose this uh, uh, at entry the height is say 19. Okay, for understanding I'm giving some basic example. Suppose at the entry of the water, suppose the height of the this point is say 19 meter, and this point is say 10 meter, for example. Okay, now what is the difference between these two point? 9 meter. 19 minus 10, 19 minus 10 is equal to 9 meters, say. So because of this 9 meter of head difference, water flow from left to right. Fine, it is clear to you. Okay, and this particular 9 meter, which is equal to what? H equal to 9 meter. That particular h can be divided equally from between these 2 points. That is, say the head difference between this point and this point is say 3 meter. Head difference between this point and this one is 3 meter, and this point and this one also 3 meter. So 3 plus 3 plus 3 is equal to 9. So total become 9. So we know that total is 9. So we can make we can draw some line at each point where the potential drop is constant. Okay, so that's why they are known as equipotential line. Since the delta H, the head difference between this point and this point, is equal to the delta H between this point, or you can say this zone and also this zone. So if you continue, it will go like this, equipotential line. Fine. So this is the significance of equipotential line. So here I can also written equipotential line represents contours of equal head. Okay. Fine. So another some important term are given here for related to your flow net. Let's discuss about that. Okay. So basically some general definition of flow net is also given here. So a flow net is a representation drawn to scale of the path taken by water in passing through soil. It is made up of flow lines and equipotential lines. Okay, this is a general definition of flow net. You can also find different definition in different book. You can also go through that also. A flow net is a representation of path taken by water which is drawn to a scale in passing through a soil. It is made up of flow lines and equipotential line. Okay, okay. So this is all about today class. Okay, still there is some thing that need to discuss related to flownet. We'll discuss in next class related to some basic property of flownets. Okay, we are going to discuss in next class. Okay, okay. So here I want to close my meeting. Okay, wait. I'm just stopping my sharing. Okay. Okay then. So now I hope it is clear to you. It is not that tough. If you got any doubt, you can also text me or call me. It's better you text me, okay? If you get any confusion, so I'll give a clarification. Fine? Is that clear? And yeah, then I'll just take your attendance now. Fine? Before that, I'll just stop my recording here. Wait. I'm going to stop my recording now. Thank you. Wait.